Welcome back to 3 Inquisitive Kids. In this video, we will be talking about a very interesting topic. Why does proof matter? And this is Chapter 7 of our 8th grade math lesson. Our course outline for this unit is our first lesson, Why does proof matter? And then we're going to be going through a series of lessons talking about definition and proposition and derivation. So here, instead of this E, it should be spelled as a proposition. In this chapter, we're going to be doing a lot of abstract mathematical thinking rather than just learning new mathematical concepts. Our learning goals for today is to understand what derivation is in math and be able to use mathematical strategies to verify propositions and determine if it's right or wrong. Now I want you to observe. Are the middle circles the same size? It seems like the circle on the left is bigger than the circle on the right. But they are actually the same size. Our brains and eyes are tricking us into believing that the left circle is bigger. Here we have line segments AB and CD. It feels like AB is longer than CD, but in reality, they are actually the same length on this page. Now I want you to look at this image. Is it moving or not? You might think I'm tricking you because, of course, you are listening to me in a video. But now I want you to pause the video, and believe it or not, it's still going to be moving. Weird, isn't it? This is an optical illusion. And now I want you to focus on the dot in the center, this black dot, and then move your head forwards and backwards. Is something strange happening? You can see that the wheels on the outside are rotating as you move your head back and forth. Now I want you to look at this image. Are these columns round or rectangular? Now here's another one. I want you to count the black dots. How many black dots are there? Now in this image, these horizontal lines in the picture are actually parallel. It may seem like that they are curving and bending, but if you take this line and you bring it down without rotating it, it's still going to overlap with another line, which means that these horizontal lines are parallel. Introduction. To determine whether a proposition is correct or not, observing, hypothesis, and experimenting is not enough. We must go through a thorough, step-by-step proof to back our propositions up, or back our statements up. So, if you don't know what a proposition is, that's a very fancy mathematical term. A proposition is kind of a statement. And a proposition might have a structure like, if this, blah, 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 therefore, or then. Usually in math we use the word therefore, our conclusion. So this is the condition, the given conditions. I'll write that CON for short. And therefore something something. This is our conclusion. Which line segment is longer, A or B? And which line segment is on the same line as D? So your eyes may think that line A is longer. In reality, line segment A equals line segment B, and B is on the same line as D. Great mathematicians make mistakes too. Here we have this mathematician, and I'm not even going to try to pronounce his name because I'm probably going to get it wrong. And he said that when n equals 0, 1, 2, 3, and 4, this expression, 2 to the second to the nth power plus 1 equaled 3, 5, 17, 257, 65,537 respectively. And he noticed that all of these numbers, all of these results, are prime numbers. So then he said, when n is a natural number, the value of this expression is always going to be prime. And then later, another mathematician came along, and he said when n equals 5, remember, this first mathematician only stopped at 4. This second mathematician went on just one more and said when n equals 5, this expression equaled this really large number. And this really large number is equal to 641 times 6,700,417. Which means that when n equaled 5, this proposition was not true. The product wasn't a prime number. So from this example, we can learn that giving counterexamples is an effective way to prove propositions wrong. all you had to do was give one example or one special situation where this proposition was wrong, and that would bring down the entire proposition. First observe, then verify. We have three figures over here. I want you to ask yourself these three questions. At first, it may seem like the solid lines are curved in this triangle, and A is slightly longer than B, and AB and DC are not parallel. Well, if you had a ruler or something, we will find that the solid lines are straight, A and B are the same length, and AB is parallel to CD. So sometimes our brains and eyes may trick us into believing something that is not true. Therefore, observation, so just looking with our eyes, is not enough to draw a mathematical conclusion. The most accurate conclusions can be established if we have, here it's not through, it's thorough mathematical reasoning and scientific experiments. So, for example, if you're doing a geometry problem on a test, let's say, and the question is asking you to find the length of this specific line segment, you can't just get a ruler and try to measure it to get the answer, because most of the times the images are not drawn to scale, which means that they aren't the most accurate drawings, which means that you have to use your mathematical thinking and abstract thinking and logic reasoning to figure the answer out. When n is a natural number, does the algebraic expression n squared minus 5n plus 5 squared always equal 1? Solution. When n equals 1, this expression equals 1. When n equals 2, this expression equals 1. When n equals 3, this expression equals 1. And when n equals 4, this expression equals 1. But when n equals 5, this expression equals 25. And that does not equal 1, which means that this algebraic expression, n squared minus 5n plus 5 squared, does not always equal 1, which means that the proposition is incorrect. As you can see that whoever did this solution planned to keep going on forever and do a lot of calculating and see what will happen if n equals 1, 2, 3, 4, 5. If when we reached 5 it still equaled 1, there will always be a number greater, and you can always go to the next number, and you will never know what will happen. So as you can see, giving multiple examples is not a very reliable way to confirm a proposition. There are an infinite number of possibilities. A good way to confirm a case is to verify a special example. So in this case, all you had to do was find the special situation where n equaled 5, and that would prove the entire proposition wrong. So just this one example proved that this proposition was wrong. As shown in the figure, there are 4 line segments coming out from point O, and we're given that OA is perpendicular to OC, and OB is perpendicular to OD. And there are 4 questions that go along with this problem. The first question, if angle BOC equals 30 degrees, find the values of angle AOB and angle COD. So if you look at this problem, you might think, oh, it's obvious. Angle AOB and angle COD both equal 60 degrees. Well, no. You have to go through very careful, very specific mathematical solutions in order to state your thinking clearly. So here we are given that OA is perpendicular to OC and OB is perpendicular to OD. Therefore, angle AOC is equal to angle BOD because they both equal 90 degrees. And because angle BOC equals 30 degrees, angle AOB is equal to angle AOC minus angle BOC, which equals 90 degrees minus 30 degrees, which equals 60 degrees. And it's the same thing for angle COD. So now that they both equal 60 degrees, we know that angle AOB equals angle COD. But of course, the question is only asking for the values of angle AOB and angle COD, not the relationship. And here, you might see that there are 2 different signs with 3 dots in them. The first one is kind of like an upside down triangle. This sign means because. Because this, therefore, it's the second sign, our thinking. So here we wrote down the given information, and then here we wrote our thinking. Question 2. If angle BOC equals 54 degrees, find the value of angle AOB and angle COD. This time, I want you to pause the video and write out your mathematical solution in that format. This is truly the language of math. So in this case, the values of angle AOB and angle COD would be 36 degrees. So after question 1 and question 2, what did you find? After looking at question 1 and question 2, we can find that no matter what, angle AOB will equal angle COD. But now you have to use math again to prove why these two angles will always equal each other. So now again, I want you to pause the video and try to write out your mathematical solution in that format. This question might be slightly harder. Solution 4. So because angle AOB plus angle BOC equals angle AOC, which equals 90 degrees, and angle BOC plus angle COD equals angle BOD, which equals 90 degrees, if these two expressions both equal 90 degrees, then we can rearrange them in another equation. Angle AOB plus angle BOC equals angle BOC plus angle COD. And then we can subtract angle BOC from both sides to get angle AOB equals angle COD. So first we observe, then we measure in experiment. Then we have a hypothesis. And then after a hypothesis, we have a conclusion. But we have to prove our thinking in our conclusion. So that's where the math comes in. You have to write it out in this format. So today we learned about why does proof matter. And we know that mathematical conclusions must be drawn specifically and exactly. And some strategies we learned was, first, we can test out examples, but we know that this is not always really reliable. And we can have reasoning for backup, or we could give a counterexample. So these were the main points we learned in this lesson, and I hope you'll come back for lesson 2.